Well, first I want to thank the organizer for inviting me here, Professor Alexei, Professor Dan, and Professor Aparecido. Thank you for giving me the opportunity to come here and talk about my work. Title a little bit different because it's only half an hour, so I'm going to concentrate in our methods. And this is a method we are very excited with. And it has several versions, so I'm going to present some of them to you today. And this is joint work. Oh, this is me, and then there is many people. And what I'm going to present, the core is in a paper with Yalchin, FNDF at Texas A&M, and also KAUST, INTERPORE, NUMPORE, and then Tom Howe in Caltech. So this is what I'm going to present. But these things is a result of talking to many people and collaborating to many people, and here's some of them. Like there is Victor Callo, also from KAUST. Mary, it was in KAUST, is not anymore in KAUST. People from Texas A&M, Rachel Lazaroff, Michael Prescio, students at Texas A&M, Wan Lian Lee, Yi Wei, and many people. Collaboration also with Marcus Sarkis at WPI, and people from KAUST. So I'm going to talk about what we call generalized multi-scale finite elements, which is a version of a finite element method in a two-grid finite element. It could be more. And it's originally introduced by FNDF and Tom Howe, but we improved some of the things you're going to see. So let's go. So I can go like this. OK, this is my line, probably ambitious for half an hour, but let's see how it goes. So let's just go. Then I'm going to present the kind of problems we're dealing with, and how do we think the cost can be set up. And then we're in porous media, so we have multiple scales. That's the problem. And usually you have grid that resolve some of the scales, but you want to include effects in all of them, right, in the solution. So that's what you want to do. And for example, I'm going to go to elliptic equations. That's going to be the example I'm going to have in my mind. And this is just a pressure equation, where you use pressure on a porous media, Darcy law. And then I'm going to consider right away a parametric problem. So I have a family of permeabilities, family of models I want to solve. And then I would like to have solutions, a procedure to solve all of them for any value of the parameter, right? And I want to solve fast or efficient in a good way. So I have equation plus boundary condition. The coefficient of permeability could be multi-scale. It could have variations in several scales. In particular, it can have high contrast, two different values, two or more different values with a very high ratio of difference. So, and then what you want, for example, in this example, I'm going to talk about the other ones. What you want is a procedure to solve fast, right? So given a value of the parameter, you set up your medium, your coefficient, and you want to solve fast with few degrees of freedom. That means you want to solve not in the grid, you resolve the coefficient because it's too fine, that wouldn't be a good idea. So what you want is to solve in a coarse grid very fast, right? With as few degrees of freedoms as you can get, good solutions. Or what you want could be, if you have to compute the fine solution, well, you have to do that. And what you can do is you can implement an iteration, but you want that iteration to be fast. And if possible, we're going to do that independent of the parameter. So for each parameter, you want to know how many iterations you need to get some accuracy, right? That's what you want in this example. And this is not just for parametric problems. It's also for many family of problems. For example, for nonlinear problems, if you think about it, when you solve a linear problem, what you do is you linearize or do some iteration. And in each iteration, you have to solve a linear problem, right? And then what you can see that linear problem is a parametric problem with this, like this, right? And if you have a good solver for a family of equations like this, then you can get through the iteration very fast, through the nonlinear iteration very fast. And then here the parameter is going to represent all possible values of u. That's how you usually do numerical upscaling or numerical homogenization, right? Usually this parameter is, for example, the mean value on a region of your solution through the iteration. So if you can take account of that, then you will have a good solver for your equation, right? Time-dependent problems is the same. You will have to solve a family of nonlinear problems. So if you have a good solver for those, you're in a good way. So this is more or less the problems we are dealing with. So we have a forward model we need to solve for values of parameters, and we want a solver that is good for all parameters, right? That's the kind of problems we deal with. An example is a parametric elliptic problem. The way we think of the course is we have two steps. One we call offline, where we do offline computations. One we call online. So more or less in the offline computations, we can spend time computing, and we can use whatever you need, right? This is an idealized way, right? And in the online, when you really have to go compute, you need to compute fast, right? So that's the point I want to make. So allow me to exaggerate here to make the point stronger, and this is more or less the setup, right? So in the offline steps, you can compute as much as you need in parallel, probably. That could be good, and you can spend time, and you save some data, and then you want to do computations online, you don't need much, right? You just need access to the data you computed offline, for example, spatial vectors or spatial solutions, and then you compute fast, right? So that's the idea. This is more or less the family of problems we deal with, and the way we think of the cost. So we pre-compute something, we store it, and then compute online when we need. We use model reduction ideas. So basic the ideas of model reductions is the following. Well, I already told you many problems, not only linear problems. And then you want to use, for example, multi-scale methods or iterations, right? So the idea is to use model reductions and then to incorporate those model reduction techniques in multi-scale methods. We're going to talk about it. So the problem, a little bit abstract at this point, could be this. It could be, I have a family of functions. For instance, all possible solutions of my equation, right? And then that's a manifold or a space, probably linear. And then I want to reduce it, right? So I have all possible solutions for each value of the parameter. For example, I have a solution. And I want to reduce the dimension of that set or that linear space, for instance, right? So I want to construct a small space with some approximation properties of that for each value of the parameter, should be mu here, sorry. I have a coarse representation of, or representation in that space or in that submanifold something with some relative error that is small. So that's the idea. That's the abstract way we think of the problem. You can, I'm going to show you a simplified way to see that problem is the following. You have all possible solutions, like if you discretize, they are vectors. And what you want to do is some reduction to give you the important ones or some subspace that generate the important ones, right? So that's basically, and there is many ways to do that. You know that already, right? So again, well, the error, the delta is the error. They have to be robust. That's independent of the parameter. And the computation of that coarse representation have to be fast, right? For instance, after you have that space, when you are given a value of the parameter, you want to compute the solution, you have to be fast. You can select subspace and Galerkin project on that, for example, if you are doing finite elements. Or you want to use that to improve domain decomposition methods and converge fast, or well, whatever you need to do with those, right? So there is several ways to do that. I'm going to give you examples. People does. And then my example is for the parametric problem. This is the weak form. And then here what you want to do is to set up something that for any value of the parameter, any good right-hand side, and any good boundary condition, you can solve fast this linear system. If you do finite elements for this problem, you have a linear system you need to solve, right? And then B is going to change with F and G, and A, the matrix, is going to change with mu. You want to see, it should be A mu here. So this is the space of parameters you want to solve, coefficients and right-hand sides and boundary conditions, right? And K might be multi-scale. So one thing you can do is to work in the global domain. We don't do that, but that's why it's in red, is the following. And you can prove that these are the best thing you can do. If you have only n degrees of freedoms, what you do is you solve, it shouldn't be this integral here, you solve an eigenvalue problem in the whole D, right? And then you choose n of them, and then you project on those, right? That's use orthogonal projection in the eigenvectors. And then that's an example of this reduced space, right? The space of all possible solutions is all defined grid functions, and you have to take the eigenvectors. The problem is this is expensive, right? That's just an example. So other example you can do is the following. You generate some right-hand size, right? There is ways to generate those. And you solve your problem. You store your solutions. Those are vectors. And then you do some POD, some proper orthogonal decomposition, or some principal component analysis in those. And then you generate with those space, with important ones, right? You can do that. The problem is global, it's expensive. This is more feasible than the previous one, but it's also global problems. So you can even generate this right-hand side randomly, right? That is on randomized SVD decomposition. It's more or less like that. You generate this right-hand side randomly, compute the solutions, and in the solution you do some principal component analysis. And those are approximation of the global eigenvectors. There is many methods like this, but all of them are approximation of the global eigenvectors in some way, right? Okay. This is basic model reduction ideas. I give you 2 examples. What I'm going to do now is I'm going to switch a little bit to multi-scale methods, 2 grids methods, and then I'm going to combine both of them. So multi-scale methods has many multi-scale methods. I'm going to present a version of the classical multi-scale method by Tom Howe and FNDF. And it goes like this. You have an equation in a fine grid that you are not allowed to solve because it's too expensive. And then what you do is you introduce a coarse grid, right? And then you want to solve on degrees of freedoms on the coarse grid. The classical multi-scale method is a version of numerical homogenization if you want. What they do is upscaling rules, they go hidden in basis functions. So you don't use normal finite element basis functions, but you use special ones that incorporate subgrid effects, right? For example, here you go to construct the basis functions for these nodes, you go to neighborhood, and you solve a problem, usually related to the global problem you need to solve. And then you construct a basis function. The problem here is you have to put some boundary condition, and that it's going to cost you if you don't use the right one. But this is one way to do it. And then the space you project your solution is generated by those basis functions, right? That's the classical multi-scale method. The problem is, for the analysis, you have to assume some relation between the grids and the coefficients. And then that's the part we improved of these methods. We don't use that in the new version. But the idea is that we need to do information, to capture information locally in the way of basis functions, right? And then this is a version of numerical homogenization. People that like homogenization, they like to, instead of doing that, they compute effective parameters. So they compute only one number for permeability in each block using some upscaling rule. And then they solve that equation with those homogenized coefficients. The problem is that for each equation, you need different upscaling rule. If you upscale Darcy, you need some upscaling rule. If you homogenize or upscale Brigman, it's different rule to compute those coefficients. So it's complicated. What we have is kind of applicable to many problems. Right. So this is classical multi-scale. It has some issues, some problems, some advantage. I don't want to go here over them because we don't have time, but basically, one thing is to choose the boundary condition. It has to be chosen properly. If not, you won't get good results. And there is many other things. And there is, this is for conforming elements. There is multi-scale methods for mixed elements, for non-conforming elements, for discontinuous, and for many other discretizations and problems. So I don't want to go over. But, well, one of the problem is if you need to choose good boundary condition, and that's not easy to do and depends on the problem. So what we did was we combined the two, because a model reduction you can do, but you cannot do globally, but you can do locally, which should be not as expensive as doing globally. And you can use some multi-scale method ideas. So the idea is then that problem of reduction is to do it locally, right? So I have the space of all possible solutions, but only on the coarse grid. And I want to reduce that space with any of the methods I gave you or any of the methods you can think of. And then we need some rule to compute for each V, coarse V, with some relative error. And the idea is I have the total space of possible solutions in a piece, and then I reduce that to V0 of in that piece of the domain, and then I use that subspace to construct the basis functions. Yeah, this is kind of automatic. It doesn't depend on the problem. You just have to choose how to do the reduction, but we have some rules to do that are quite general. But the idea is that combine the two. Then model reduction locally and use that information to construct basis functions. Simplified view of the problem is you have global functions. Then you look at all possible values in a neighborhood. That means a piece of those vectors. And then single out that part, and then reduce that. Do some principal component analysis, and then you have some important information of that part, and then you put somehow together all the pieces, right? Good thing about this is this reduction you can do for each region in parallel, so it's something good to have. And then that's what we call generalized multi-scale finite element. And then one example is the following, which is, well, this is more or less the general setup, right? So you have offline computations where you think about the space of all possible solutions in a piece, and you reduce that to initial subspace. And then when you go online, that means when you want to compute, you take particular value of the parameter and you can project in those spaces or construct basis functions, see? Yeah, that's what you do, using the offline information. You can reduce even further if you can do it fast. Example. One example you can do is, for that problem you saw, right? So you have neighborhoods, so you want to construct basis functions here. What you can do, which is kind of expensive, but it pays off, and we simplify that later, is the following. We take the eigenvectors only here. So you solve eigenvector problem related to the operator you want to solve only in this piece, right? So you take important eigenvectors, and for example, you can do is the following. You multiply them by partition of unity to make it conforming to the finite elements, and then this is your space. The Galerkin space is going to be the space generated by those functions, right? Then that's the coarse space. For example, you can compute a coarse solution of this only with the degrees of freedom you select. And this is kind of different to the one before, because before there was one basis function in each piece. Now we have as many as we need. And we do analysis with this, and the error is going to depend on how the eigenvalues that you solve in this piece decay. And it's going to be proportional to the first eigenvalue you left out, right? So if you select the proper ones, you have good error estimates. And we can study how it decays the eigenvalue problem and how many we need, those we can do, right? And you can do any of the things I showed you before. For example, you don't need to solve the eigenvalue problem. You can do what you saw. You can generate some right-hand sides, compute the solutions locally, and then reduce those, right? Which is approximation of the eigenvalue problem, but it's faster, right? So you will have in each region basis functions. You may have several of them in each. And then that's the space you're going to generate. And we have error estimation and everything, right? This is just, I'm going to stop here and give you an example. So this is permeability. This is several values. It's what we call high contrast, which is two values, and then it has a background 1 and values very high, which is discontinuous. And I have agreed like this. It's not aligned with the coefficient, which is easier when it's aligned. And then this is the fine scale solution. Compute at the resolution you resolve this, right? This is what is computed by the classical multi-scale methods, and not a little bit more costly and advanced little multi-scale methods called energy minimizing functions, which is hard to do. And these three are versions of our methods. And then we compute errors, of course, but here I don't have time to go over the numbers. So picture is, I hope is enough to, to motivate you. And then this is our solution with the eigenvectors. And this is with an approximation of the eigenvector, not even the eigenvector problem solving locally. So an approximation similar to the one you saw at the beginning, generated some right-hand side, right? So then for parametric problems, you would have to do a parametric eigenvalue problem. Then what you do is an approximation of that using model reduction. For example, you can use a reduced basis approximation of that parametric eigenvalue problem. And this is, I don't have time to go over reduced basis approximation, but all you need is an approximation of the eigenvectors, right? So all you need to wait to approximate for each value of the parameter the eigenvector problem, right? So we can do for parametric problems, and this computation of the approximation, initial approximation of the eigenvector is the one we do offline. right? Then after that, we have initial approximation, we go out to compute online. There is many options. For example, you can choose in each region boundary conditions, and from those available boundary conditions you solve, you store the solutions, and do some principal component analysis in those stored solutions, or some POD or PGD, whatever of those model reductions, right? Or usually what works better if you choose to solve in a region a little bigger than the original region where the basis function is supported. We call this oversampling version, right? And then here, if we do randomly, for example, some random right-hand sides and solve here local problems, you can do this in parallel and reduce those, we have good results, right? And we can prove with some randomized HBD estimates, we can prove our error estimates when you use this kind of basis functions. Then the idea again is locally in a piece, you do model reduction, right? You generate some basis and reduce. And then there is an initial step we do offline, which is recognize a small space of all possible solutions. And then we go, this is the first step, and then there is we call it spectral selection or some approximation of the eigenvalue problem. And then one thing is you have to choose a good inner product to do that with good energy. But we can do that. Usually it's an average energy or something. And then online, you can project in that space. So if you have time, you can reduce even further, solving some or doing some spectral selection that involves the particular value of the parameter you need to do, right? So this is more or less the idea of the methods. If I have time, I can go over one application, for example, or I can just go straight to conclusions. I don't know. Okay. So this is just one application. We worked with someone at Texas A&M on linear control problems. He's well, the linear control part is the one that understands well. And then the problem is this. You have equation, parabolic equation with a coefficient complicated like the one you saw. It's not parametric problem, just a single coefficient. And then you have some input parameter in a small dimensional space, right? So it is an input or control, and then you solve and get the states. And from the states, you measure something. You measure, for example, n quantities. N is a small dimensional. Then this problem goes as follows. You have some input and some observed quantities, and the input is low dimensional, and the observed quantity is also low dimensional. But to compute, you have to compute to solve a finite element problem in a very fine grid, right? So there is what you want is to simplify that problem. There is a mapping here for low dimensional input to low dimensional observed quantity. Right? You want to simplify that. You don't want to go through solving a parabolic equation in a very fine mesh to do that. So the way to do that is, well, if you discretize, this is the problem. This becomes matrices. In the particular case, this f is linear. If not, well, it becomes some function. And then what you want to do is to have a surrogate model for this, some model where you have some low dimensional parabolic equation that you solve, and then you can go through from inputs to observed quantity easily, right? But you have to have a good model here. If you don't have a good model, you won't get the behaviors you want from input to outputs, right? So what people does in balance truncation to simplify that mapping is, balance truncation, what it does is compute two Gramians, P and Q, that are solution of these Lyapunov equations, and then they compute some singular value decomposition of this matrix, right? And then the important eigenvectors or singular values of this matrix are the space where they can project this equation, right? And then they will have this reduction, right? But then look at what balance truncation does. You have to solve these Lyapunov equations, and these A are very high dimensional matrices, right? Probably symmetric, that's fine, but very high dimensions, you don't want to do that. So one way to do is apply our methods, and instead of considering this equation to do this reduction, you consider a coarse model. So this A0 is a projection, this should be minus, sorry, projection of A onto the space generated by those basis functions constructed using local eigenvectors. So, and then you can compute, instead of doing the fine grid model, you can compute this model. And then you can go to do the Lyapunov equation on the fine grid, which has much small dimensions, and you can do, right? And this is just an example. And example is interesting. This is the permeability we use. and then the input are some right-hand side, and the observed quantity is the mean pressure in a coarse grid, right? And this is more or less what we have. This is at some time the observed quantities if you solve the fine model, right? This is the observed quantities if you solve only the coarse model. The fine model is 10,000 degrees of freedom. The coarse model is 156 degrees of freedom, right? And this is the observed quantity, which is very similar. The three are very similar. We have the numbers there, which I'm going to show you. If we do the balance truncation on the coarse model, which is possible because this is matrix are small of the dimension of the coarse grid, actually 156, right? Doing the balance truncation here in the fine model is you have to solve the Lyapunov equation. That's costly, is high dimension. Well, if you can do, but usually it's too expensive. And then this is and then here the equation, the parabolic equation, it has only dimension 10, but still you have what you need, right? And the point here is if you don't have the right coarse model to do the balance truncation, it doesn't work. For example, this is our method. This zero means we use normal basis functions, no eigenvector, no additional eigenvectors. And then we saw some errors. This is error in the L2, little L2, discrete norm. This is error in weighted L2 with the K to get the coefficient. This is H1 error. This is from the states, not the observed quantity. This is error in the states, in the U, in the solution. And then if you use, this plus zero is normal classical multi-scale methods. Error is big, right? So if when you do the Lyapunov equation on the coarse grid, you don't have the right subgrid capturing, you will waste the Lyapunov equation, you will waste the balance truncation procedure. So you need really the right degrees of freedom. So if you add, for example, 2 eigenvectors in each, we can do it in an adaptive way. It doesn't need to be the same, but here we add 2 eigenvectors in each, and we have really good errors from the balance truncation model to the original fine grid model, right? And then in the middle is our coarse model, but you cannot do that. You won't have good errors if you don't have the right coarse model in the middle. So that's basically what I wanted to tell you. Plus some final comments. I gave you basically linear elliptic equations as examples, but there is the randomized algorithms where you don't have to solve eigenvalue. You generate some random right-hand sides and solve. We have error estimates for those. We can do, there is people that apply this to wave propagation, not me, someone else, somebody else. So for example, to DG framework, because all I show you to you is conforming finite elements, you can do DG and adapt. Depends how many eigenvectors you need, depends on the coefficient in each block. We can upscale Brinkman, for example, which is difficult because Brinkman has Stokes, has parts that behave close to Stokes, part that behaves close to Darcy. So people that upscaling needs a special upscaling rule depending if it's Stokes dominated or is Darcy dominated. But here we do automatically, it doesn't matter if you are in Stokes regime or Darcy regime, right? We can do for mixed methods. We can combine, for example, with balance truncation or other model reductions. For example, there is a model reduction called discrete empirical interpolation method, which is suitable to apply in conjunction with our generalized multi-scale finite element. This is what is already done, and this is some of the things we're doing. We're doing linear elasticity, some interface problems with also upscaling rules, depends on the condition you have on the interface. But if you do it like this, it would be automatic. And then conservative framework, you need sometimes finite volumes for conservation and those stuff. And further development for nonlinear problems and further analysis. We have error estimates in many cases, but we're trying to improve the analysis to make it neater because right now it's a bit complicated to go through the proofs. So we're trying to make it more friendly, at least the analysis, because computations already many experiments. And that's all. That's all I wanted to tell you. Thank you for your attention.